Good morning everyone, and welcome back to our channel. Let's continue with our course on CNC programming. In the last lesson, we saw that we can move in G0, G1, G2, and G3, thus in a linear manner, in rapid linear motion, in working linear motion, and in a circular manner. These are the interpolations. Linear interpolation and circular interpolation. As you can see today on our screen, I see it on the right. I don't know if you will see it flipped on the left. We have programming examples. Examples of programming that can put us in difficulty. Let's look at the first one, which you have a bit larger on your screen. We have a radius, but we do not know the starting point, and we do not know the end point. The only thing we know is that it is a junction, meaning it is perfectly tangent at this point, and at this point, well, with the programming we have studied in these days, we need to discover either this point, or the center of our radius. This requires knowledge of trigonometry or the Pythagorean theorem, or the use of CAD to be able to draw something so simple, nothing transcendental. Fortunately, I tell you that until 25 years ago, it was also the only path we could take, so doing trigonometric calculations and discovering the various points. Today we are luckier. They have invented, to the joy of us programmers, Greta programming, which is a programming that simplifies our lives in complex profiles and allows us to use the fillet and chamfer, angle, function. Charity is trivial, but it can be done in a much simpler way. That's why we start to see direct programming. Then we will do some examples. So first of all, angle function. If I am at a certain point, let's say I am at x100 z0, I can tell my machine to move at an angle. Let's say I want to make a chamfer at 45 degree. So I give it the angle, not 45 degree. I will tell you later what I give it. But I say I want a chamfer at 45 degree in here until x 110. The machine starts at 45 degree and will stop at x 110, regardless of the arrival z, meaning it will have this as a barrier and will be determined by the travel angle and the x where I tell it to stop, or I can tell it the angle is z minus 10, so it will have this as a barrier in addition to the travel angle. How does a lathe traverse angles? A lathe reads angles this way. If this is my Cartesian coordinate system, this is angle 0, and this is the positive direction of travel. So these will be 45 degrees. These will be 90 degrees. These 135. 135 is the angle I will use to make most of my chamfers. 180 degrees. 225. Let me make the calculations. Incorrectly, and approximately 315 if I want to give the degrees in a negative way, which can be convenient when I do operations going back. Therefore, I will have minus 45 degrees as well as minus 90. degrees, and so on. Okay? Then, as for programming purposes, specifically speaking about it now, it is normally done with an A representing angle, or in Fanuc systems, in more recent Fanuc models, A, while within Siemens, you use ang head, ensuring that you understand this concept clearly. The concept is what needs to be learned, not the mathematical letter that is placed in front of it. The same discussion applies when let's take a small example, have to go from x0, z0, x20, z0, z10. Here is a profile with a perfect corner. Since I want a chamfer of 5x5 here, so it must be a 45-degree chamfer, not slanted, but a chamfer of 1x1. 2x2, in our case 5x5. So I will go here and set it to C5. In Fanuc up to 2005, 2007, 2008, C5, in more recent Fanuc models, it was a requirement that came, if I remember correctly, with powered tools. Or I need to read it because I don't remember CHR5 in Siemens. So, Fanuc, what does the machine do? The machine reads this. I have to go from x0 to z0. I have to go to x20, z0, c5, okay? So I will cut the trajectory by 5 meter on one side and the other. So even if this line had been slanted, the cut here is perfectly the same. The C works, okay? We will do some examples. Examples always help. The same discussion applies to a radius with a fillet, not with a radius, with a perfectly tangent fillet from the entry point to the exit point. Then we put an R here, and here we put R and D. It seems to me I need to check because I don't remember Siemens by heart. Because Siemens, I will show you, is programmed a lot with an internal CAD CAM R&D, and it gives me the radius. What is it then? ECS, if I remember correctly, the radius is X. Anyway, LCs, for example, I'm sure that the radius is exclamation point, array. So what you need to understand is this little formula. Coordinates followed by R and D. That is, the code that transforms the destination point, instead of a sharp edge, into a radius rather than into a corner. That's the concept. Is it not clear to you? No problem. We will now make some beautiful examples. And I have quite a few to do, because, in my opinion, these are the examples. Remember, this angle, 0. The opening, angle, direction. Okay, the first example only involves a simple radius, which is what I showed you earlier. Let's forget about G1, G2, G3, G4. Let's just say it's all in G1. Let's only consider the path of this profile from here to there. So, I also look there to see what I do first. So X20. Then we have Z20. And here we have an X50 in Z that remains at -20. X50. But we have a radius of 10, R10, R10, At this point, double coordinate x 70. The minus 40. If I hadn't written R10, the machine would have done this. In meter R10, remember that lathes do not read block by block as you do, but they have already read the next 10 or 5 blocks in order to calculate the path. So the machine says 0, Z0, X20, Z20, X50. I have a radius of 10. Let's start doing it and go tangent to this line relative to this point. The rule is, looking at a drawing, if you can draw it, you can program it. And indeed, what would you have done with a small ruler? You would have done this. You would have drawn this line then, a line like this. You would have taken the 50, the 70. You would have made at least 40. You would have drawn a line with the set square. You would have taken the set square and fixed it in such a way to do this and that. You would have found the center and used the compass to draw the line. Actually, to tell the truth, you would have taken the set square, made a parallel line of 10 millimeter, a parallel line of 10 millimeter, found the center, and made the radius. My goodness, it turned out terrible, but redo it. If you had a set square in hand, you would have drawn a line, a line, a line, a line. It's parallel to this one. The parallel to this one found the center, and with the compass, you would have made the radius. Then you would have highlighted the profile, which is an essential step in the process. You can either draw it manually, using traditional tools, or program it using modern software techniques. The next one is very simple in its design, but it is also smooth and elegant. So instead of using complex methods, we could easily do it point by point, because the coordinates are easily obtainable and straightforward to work with. For example, the coordinates are x0, z0, z20, x50, c5, z40. It is obvious that this could have been programmed in multiple ways, utilizing different approaches and techniques. So from here, starting at z20, you could proceed to x40, z25, x50, z40. And this is now considered an old-fashioned method, yet it remains effective. Or you could do x40, then x50 at 135z, minus 40. z40. So what does the machine do? It arrives at x40 and says, okay, now I have to go to 135 degrees, but I have to stop at an x50, so I stop here. Okay, so I would say this is really a very simple example. Now, let's go. I had already mentioned this to you. Let's see. Where do I have the little sombrero? Here it is. Exactly. Indeed. This one here, you see, is 5 by 5, so it's a bevel, x0, z0. After that, we won't delete it anymore. This one instead, we will delete it again, x30. Z minus 10. And here we have this point, so 70. Z minus 20 C5, we program. The vertex of the intersection of these two lines. Vertical line at x30, vertical line. We take z minus 10, the intersection point. We cut. The two lines, we cut them. We take our ruler, measure 5 from here, 5 from here. We can measure it, we can draw it, we can do it Let's see. This one. R5Z minus 70. Wow, we can draw it. Look at the previous one, of course. Line, small line 10. Intersect the two. Parallel lines with the ruler. This. Parallel with the ruler. This. Intersection point. I can draw it. I can do it. Perfect. Angle. Finally. We were missing it. We did something quick before. Wow. We see, with the old programming, point. The designer gives us a piece like this. We don't have this point. We only have the diameter. But we don't have the Z. The direct programming here helps us. So, the 0, Z0, Z, minus 16. At this point, sorry, I forgot the X30, the diameter. I stop at X30, go to Z, minus 16. At this point, what do I do? 60, radius opening. So minus 180, minus 60 equals 120. Therefore, X70 at 120. What does this mean? This is my X70. On 20. What does this mean? This is my I70. This is my path at 120 degree. I stop here. So the machine stops here and then goes to Z. It didn't mark. Z minus. Z. Minus 50. It doesn't matter for our case. And here, we have 60 degree or 120 degree. Degrees here don't matter much. We know that a right angle is 180 degrees. So calculating 120 is very easy for us. Or, sorry, this was the example. So, if you want to go back in the video, it's not difficult. I think it reads well. Enough here too. Same. Discussion, same piece. If I put C5 here, nothing prevents us from combining our angle with a C or an R. Because fundamentally, when I drew this, the machine knows it then has to cut 5 mm here and 5 mm there and go to make this little radius. Presumably there will be the exact same thing with the R. You see, R. What does the machine do? It makes this drawing. Then it says I have a radius of 5 here. So I need to create my parallel here and my parallel here. I find the center, I'm tangent, and I make the radius. Direct programming. I can say it. Good direct programming. Look how beautiful this is. Let's go. See it. Excellent. Let's turn it on. We leave 0 as it is, because it's the default. Let's go to X30. I could have left that too. And to Z. X then 33, because we have already done this. I'm further ahead. I made a mistake. Ah, we're here. Sorry, give me. We are doing this, so 33. And here, it is very simple. Just put a little corner once we are at X33. First we go to Z, minus 16, and here. What do we put? We have Z, so Z minus. Angle 180, 30, 150, X80. And then the Z at that point is relevant. So I am at X0. I rise to X33. I move to 16, and then from here I set a barrier at Z35 and move by 100, 50 degrees, that is 30 degrees. Well, when I encounter my barrier at theta 35, the machine stops and then rises to X80. As you can see, below it has simply made the piece a bit more mechanical, so it has added some radii and chamfers. At this point it will be very simple to modify this program. When I rise to X33, I say yes, rise to X33, but cut the end with a chamfer, C2. Then the same discussion, go to Z16, rise to 150, arrive here and build your profile, but here in the middle, R12. What does the machine do? It builds its parallel here, its parallel there, finds the center, and makes the radius. So direct programming helps us incredibly. Last example, different, a bit different from all the others. I would also say that this way, we have all seen it. I have other examples, but in my opinion, they are along the same lines as these. Yes, okay, I confirm. I confirm, yes, they are all along the same lines as these. So the last example is this. As you can see, there are multiple rays intersecting with each other. We can draw it. Let's do the opposite. Let's draw X0, Z0, rise to X50, move to X at Z minus 16. We have 15 degrees that we need to descend to. And what do we have from these 15 degrees? No, we have other examples to do. So, this is interesting. So, what are we doing here? Here we say, to descend, the angle should be 15 degrees, so 180, 170, 165, but how far do we need to descend? Well, we can't do it. 165, but how far do we have to go down? Doesn't tell us, but what does it tell us? He tells us that the next block will be at X80Z minus 35, so X80. Z minus 35. How do I get there? I get there vertically. You understand that I can draw it. Then, once I have done this, it won't be a problem to draw a parallel. A parallel. Find this point and trace the radius. Just as it won't be a problem to draw a parallel, and make the radius. This is because the machine only needs the points suitable for obtaining the drawing. So, Io, Zilo, then X50. Z, minus 16. Then, we simply say, angle 165, which will end with a circumference of 12 millimeters. At this point, the machine would go into crisis if we do not give it, in this case, X80, Z35, angle 90 degree, R6. You see that we have made X80, Z35 the angle, and the radius exist together harmoniously for the first time. In this particular instance, in the same block, that is to draw our profile. At this point, we need to add, if we don't, a Z50, because it must know in which direction to finish and complete my profile. I will stop now, but I will give you a static image. So take a screenshot of this, of these little exercises to do at home for your reference. The concepts I gave you allow you to do all this exercise in the next video, which we will do together. So the next video will be at your convenience. Video of Mio exercise. Remember the AO speech in Fanuc and ang equal in semis, and in the same order, C and CHR equal, and R and RND equal if you want to do the example in Siemens or in Fanuc. So, angle, chamfer, fillet Fanuc, Siemens Fanuc, Siemens Fanuc, Siemens. Well, next time we will continue with the examples. I thank you for being with me, and I hope to have opened you well to the world of direct programming, because it is essential. If you do not know how to do direct programming, you will not be able to program the machines. And if you have any questions in the video, please put them down so we can try to solve the problems as much as possible, because I will not be able to answer everyone.